Hey guys, what's up? Welcome back. Today I will solve an example on applying the integral form of the linear momentum theorem for the Navier-Stokes equations. So one of the forms we worked with was the following: d by dt of the integral over the control volume rho u dv plus integral over the control surface of rho u dot n ds was equal to the summation of forces exerted on the control volume. Okay. Now, with this theorem, it's important to recognize the difference between this guy and this guy. This is the momentum component being transported, and this is the net component of velocity coming out or transporting the momentum through the control surface. And it's very important to identify which is which. So this example will hopefully give you an idea of how to apply this. We are going to consider a jet, a stream that is being launched on some kind of vane that is going to deflect the flow. Okay, this direction. So this is a solid, and this is anchored to the ground. Okay, so this is anchored to the ground. I'm going to assume that the jet is just going to flow nicely over here and curve and then exit through here. Okay, so this is our jet. I'm going to assume that the area over here is A1, the area over here is A2, that we know that the flow is coming in here at V1 and it's exiting over here at V2. There's tremendous choice in how you choose a control volume. It can cross a solid, it crosses inlet and outlet boundaries. In this case, we're going to pick one that does just that because we're interested in the force exerted by this jet on the vane and how much anchoring force are going to be needed over here. So we will take our coordinate system, x, y, okay. We'll draw this control volume over here, and I'll make it cross this boundary, and then go through here, okay, and it crosses the anchor, okay. And as the fluid pushes the vane out, that anchor is going to react to it. So we're going to put a force over here, reaction force X, and a reaction force Y on that vane. Now, we are going to apply the two components of momentum and see how this works. So we start with the X momentum component. Okay, we're going to call that U, okay, U or rho U. Okay. Remember that our velocity vector field is U, V, W. Don't confuse this U with this vector U. So with the X momentum component, we get d by dt of the integral over the control volume of rho U dV plus integral over the control surface of rho U dot n ds. And that's equal to minus Rx, right? So that's the component force in the x direction. Now this flow is steady, so this goes to 0. Okay, so we are left with this surface integral over the inlet and outlet surfaces. So the integral of over the control surface of u dot n ds is equal to the integral over a1 plus the integral over a2. Now, over a1, the x component of momentum is v1, so we get rho v1. Now u dot n at a1 is minus v1 ds. At a2, the x component of momentum is v2 cosine theta, where theta is the angle between the jet and this is the vane's angle, really, and the horizontal. So we have rho v2 cosine theta, and u dot n is v2 ds. So this gives us, this surface integral gives us minus rho v1 squared a1 plus rho v2 squared cosine theta a2. Now a1 v1 and a2 v2 are related due to mass conservation, so we can significantly simplify this, but that's not the point of the exercise. The point of the exercise is to get you to recognize how you compute these rho u's. Okay. For the y component of momentum, we have a d by dt of the integral of rho v dv plus the integral over the control surface of rho v u dot n ds is equal to ry. Okay. Now flow is steady, so this goes to 0. Okay. The surface integral over the control surface of rho v u dot n ds is equal to the integral over a1 plus the integral over a2. Okay. Now, if you remember from this plot, the integral over a1 of the y momentum, there's no y momentum component over a1. So rho v, that's equal to rho times 0, okay, times u dot n, which is v1 ds, so that's all 0. Now, on the surface area over here, a2, the y component of momentum that's exiting is v2 sine theta. So we have rho v2 sine theta, so that's v at the exit area, a2, times u dot n. What is u dot n over here? It's v2, okay, ds. And that is equal to rho v2 squared sine theta a2, and that's also equal to ry. Okay. I hope this helps clarify some of the intricacies of the integral momentum theorem.